Hello students, today I will discuss compound microscope. As we know that a convex lens can produce magnified image. This is a convex lens. Let us place an object in between center of curvature and focus. The object is placed between center of curvature and focus. One ray will go parallel, other ray will pass to the optical center. Okay, the ray that passes to the optical center moves undeviated, while the parallel ray after refraction passes to the focus. These are the refracted rays, they meet somewhere here, so this is the image, and the image is magnified image. That is, the size of the image is bigger than the size of the object. In this case, the image is a real image. Now place an object at the focus. When the object is at the focus, the image forms at infinity. One ray, similar way, one ray, parallel ray. After refraction will pass through the focus. Another ray will pass through the optical center, which moves undeviated. The ray passing through the optical center moves undeviated. These two rays are parallel rays, they will meet at infinity. Now when you see from this side, okay, then you produce them in the backward direction, okay, so they appears to meet at infinity. This is actually a simple microscope. Here the final image forms at infinity. Its magnification we have calculated and is found to be m equals to d by f. M equals to d by f. This is one case of simple microscope. Now let us take the other case. This is the convex lens. Now if we place an object between focus and optical center, when you put an object between focus and optical center, like before, one ray, parallel ray, after refraction will pass through the focus, and the other ray will pass through the optical center, and this will move undeviated. These two rays are diverging rays, so they will never meet, so we produce them in the backward direction. When you produce them in the backward direction, they will meet somewhere here at this point. So this is the image, and this is called virtual image because the rays are not actually intersecting, but it appears to meet. The rays are passing this, but we have produced in backward direction and appears to meet at this point. This is a virtual image. The position of the object is so adjusted that the final image forms at least distance. This is another case of simple microscope. In this case, the final image is at d distance. D is the least distance of distinct vision and its value is 25 centimeter. The magnification in this case is found to be m equals to 1 plus d by f. Though the simple microscope produces magnified image, but the maximum magnification is 9. So the magnification for a simple microscope is less than or equal to 9. That is, the size of the image is 9 times the size of the object. Now, in some cases, if the object is very small, then even 9 times greater image is not visible for naked eye. So, to magnify more, we use two lenses. When we use two lenses, then their magnification will be multiplied. Suppose the magnification for the first lens is m1 magnification for the second lens is m2, then the total magnification will be m1 into m2. That is, their magnification is compounded. For a single lens, if it is 9, then for two lenses it is 9 9 is 81. So size of the image is 81 times the size of the object. We use this principle in constructing a compound microscope. A compound microscope consists of two lenses. They are called objective and eyepiece. The lens which is nearer to the object is called objective, and the lens which is nearer to the eye is called eyepiece. Another thing is the focal length of objective is less and the focal length of eyepiece is more. Let us draw a simple Let us draw a compound microscope. This is a convex lens which is called object, which is called objective because it is placed near the object. Say AB is the object. The object AB is placed just outside the focus of the objective lens. Now, as before, one ray will go parallel, other ray will go optical center. The ray passing through the optical center moves undeviated, moves straight, and the ray parallel ray after refraction passes through focus. They will meet somewhere here, and this is the final image. Let us call the image as A dashed B dashed. Now for objective, AB is the object, so object distance is UO and A dash B dash is the image. Image distance is VO. Now the magnification for this objective MO is what? Size of image, that is A dashed B dashed by size of object, that is AB, and this is what? Image distance VO by object distance UO. Now we'll use another lens which is known as eyepiece. For this eyepiece, A dashed B dashed will act as a object, and the object A dashed B dashed lies between focus and eyepiece of this lens. So the eyepiece will produce a virtual image as we have discussed. This is the case when the object is between O and F, the image is virtual and at least distance. So we'll draw in the similar manner. Now one ray will pass through the optical center which moves undeviated, and another ray, parallel ray, after refraction passing through the focus. These two rays will never meet, they are diverging rays, so we'll produce them in the backward direction. They meet somewhere here. So this A2, B2 is the final image. And the distance of the image is D, least distance of distinct vision. This is the ray diagram of a compound microscope. Here the eyepiece behaves like a simple microscope, as it is shown in this case when the final image is at least distance, and for that case magnification M equals to 1 plus D by F. So magnification for eyepiece ME equals to size of image, that is A2 B2 by size of object A1 B1, and the magnification we found out this to be 1 plus D by FE. So the total magnification M is product of MO and ME. Now we'll substitute the value V0 by U0 and 1 plus D by FE. This is one expression for magnification of compound microscope. Now you see, when you bring the object AB closer to this lens objective, as it comes closer, the image A dash B dash will move away. When the AB comes closer, A dash B dash moves away. Now AB can go maximum up to F naught, maximum up to F naught, but it cannot be F naught. It cannot go to F naught because when object is at F naught, image will become virtual. So you will be slightly less than F naught. So we have taken approximately F naught. Then when the object comes closer, the image will move away. Maximum it can come up to this eyepiece. So this distance is the maximum distance. The distance between objective and eyepiece is called capital L, length of the microscope. So the maximum value of V naught is capital L. This can go maximum up to this. For object distance you have to put minus sign. Therefore this expression becomes m equals to minus L by F naught whole into 1 plus D by Fe. This expression used for numerical. Thank you very much.